In this video, we'll be looking at the second set of procedures that we get to analyze categorical data, and that is namely when we have contingency tables, a two-way contingency table, and we do a test for homogeneity or a test for independence. Let me explain. In this chapter, we basically have two procedures. The one is based on a one-way frequency table where you have one row and j columns, and for that we considered three goodness of fit tests where probabilities were known, where probabilities had to be calculated, and where probabilities had to be estimated, and this is covered in sections 13.1 and 13.2. In this video, part 1 and part 2, we'll be discussing two procedures for the analysis of a two-way frequency table, where instead of one row, we now have I rows, and we have j columns again. And we're going to consider the test for homogeneity in this video, and in the next one, the test for independence. Both of these are covered in section 13.3. But just as the basic procedure for goodness of fit tests are all basically the same, the procedure for homogeneity and independence, the procedure itself is also very similar. It's only the point of departure for the two that's a bit different. So, what is a two-way contingency table? It is where we have counts of frequencies which we tabulate according to two factors, the one having I levels and the other having j levels. And in the table, we have frequencies, so note the n to represent a count or a frequency, and the subscript, the first one indicates a row and the second subscript indicates the column. So this is the kind of data that our analysis will be based on. Now, based on such a two-way contingency table, there's two types of tests, and I'm going to illustrate it first of all at the hand of exercise 38 and exercise 40. The test for homogeneity, for example, will answer a question like the following. Are male and female coaches homogeneous with respect to years of experience? Or, putting it differently, are the distribution of years of experience the same for male and female coaches? Now you can see these are sport coaches, and each person in random samples of 2225 male coaches and 1141 female coaches was classified according to number of years of coaching experience to obtain the accompanying two-way table. And here you have the table at the bottom. So what's important to see here is we have two independent samples. And with fixed totals. Let's say totals N1 and N2. The total for row 1 and the total for row 2. The total for male was 2225 male coaches and for female 1141 female coaches. And now you answer the question, is this distribution over years of experience the same for male and female coaches? And this is an extension of a test that you've done earlier in chapter 10.4, where you compared P1 to P2. Now you're comparing J categories. In this case, 1, 2, 3, 4, 5. You have 5 columns. You have 5 categories that you compare to see whether it's the same. You want to see if the proportion is the same for male and female in years of experience category 1 to 3. You want to see whether years of experience 4 to 6 has the same proportion of male and female, and so on. While on the other hand, for a test of independence, we will ask a question like the following. Is there a dependence between marijuana used by students and their parents' use of alcohol and drugs? So what we have here is a total of 445 college students who was classified according to both frequency of their own marijuana use and their parental use of alcohol and psychoactive drugs. So you have a total that is fixed, 445. Here you had a total of 2225 and a total of 1141 NI. And here you have a total N that is classified according to two factors, namely parental use of alcohol and standard level of marijuana use. So on the left-hand side, in this example, you have populations that are independent and you have two independent samples from each of these populations. So you have two populations from which samples are drawn, while here you have one population that is categorized according to two factors. So here you consider two populations and one factor, and here you consider two factors and a sample from one population. And this is the basic difference between the two, but the calculations you will see are much the same. But let's get to the theory first, and then we'll explain a little more. The test for homogeneity assumes that we have I random samples from independent populations. So we have I populations of interest, and a sample is taken from each one of these populations, and you are given an example there. While for the independence test, you have one random sample, and this one random sample is classified according to two factors. So in situations of type 1, we want to investigate whether the proportions in the different categories are the same for all populations, and the null hypothesis states that the populations are homogeneous with respect to these categories. While on the other hand, in type 2 situations, we investigate whether the categories of the two factors occur independently of each other in the population. Our general notation for homogeneity is the following. We have observed frequencies summarized in a two-way table, where the rows indicate the independent populations and the columns indicate the different categories. Note the subscripts and note the total. We have a fixed total of N1 for sample 1, which was drawn from population 1. N2 is the fixed total, so these are all fixed, and they add up to a grand total of N. The number that occurs in each category, of course, are random variables. So Nij is the number of individuals in the ith sample who fall into category J. And N.J is the total for each column. It's the total number of individuals among the N sampled who fall into category J. And N is the grand total of all the samples that you've drawn. So the notation for homogeneity is we're going to work with J proportions that are compared for I independent populations. Now, the proportions within these populations will add up to 1 for each population. And therefore, Pij in this case represents a proportion of the individuals in population I who fall into category J. Now we want to compare these. For the different populations, we want to compare the proportions in the first category and in the second category and in the jth category. So therefore, our null hypothesis can be written as we want to compare P11 to second population to ith population. So we want to compare all the proportions in the first category, all the proportions in the second category, all the proportions in the last category, the jth category. So in general, we can write it as P1j equal to P2j equal to Pij for j that varies from 1 to capital letter J. All right, so just remember that is comparison of over the rows, over the populations, the proportions in each of the categories. And think about the coach example. We want to see whether the proportion of male and female is the same in the category with lowest experience, and then the next category of experience, and so on, because that will tell us that the distribution of experience is the same for male and female. Okay. So under the null hypothesis, where we then assume that all the proportions are the same in each column, it means that if we have a contingency table, and this is what we want to test, we need to estimate the proportions in these categories. Now, let the random variable, capital letter N, subscript ij, be the random variable denoting the frequency in cell ij. So that is for population I, for the ith population, the jth category. Then we can say, according to the theory, the expected value of the frequency in the first population, first category, will be N1, that's the total. Remember, this was N1, N2, and how do we get expected frequencies? We multiply the theoretical probability with the frequency, the total number in that category. So therefore, the expected value of this N11 in cell 111 is N1 times P1. In the second N12, in other words, in this category, the frequency we expect is N1 times P2. And in this category, we expect N1 times Pj. And here, N1 times P capital letter J. In the ith row, we expect the frequency in the ith row is the total in the ith row, that is our fixed sample size in the ith population. That's Ni times P1. And in the jth column, it will be Ni times Pj, and so on. And similarly for the last row. Here we have Ni as our sample total, and our expected frequency then in the first category of the last population is then that total times the probability of an observation in that column. So we are still going to have the same N1 here again, just as we had with the goodness of fit tests. The observed frequencies and the expected frequencies should be the same in the end. So we have to estimate these such that this will hold. So given then that these are our expected frequencies, and when the null hypothesis, we know that this is true, how can we estimate Pj? Now remember, Pj, P1, if I go back, can be estimated from any one of these. So what we do is we estimate P1 as the total for this column divided by the grand total. In other words, we get the average, the estimator of P1 is the observed frequencies in the first column divided by the total number of frequencies, all added together in all the populations together. So your estimate for P1 is observed frequencies, the total observed frequencies in column 1 divided by the grand total. And once you have that, you can multiply to get your expected frequencies. Your expected frequencies then in each cell, in cell 1, for example, is then the total for that row times the estimate for P hat, the estimate P hat for that column. And that is row total, which is your sample total for population I, times column total divided by grand total. And that's it. You will have observed frequencies from your contingency table. In this way, you get your expected frequencies in each cell, and you can test how the expected frequencies compare to the observed frequencies. So here's our test. For homogeneity, we compare the proportions in a number of categories over several populations. And within each cell, we estimate the expected count, and that expected count is then the total for that sample times the proportion, an estimate for that proportion, which is PHJ, and that's just a column total divided by the grand total. So what you see is we have ith row total times the jth column total divided by n, and that's how you get your expected frequency, and this is also what you will use for the test for independence. So for each cell, the observed frequency can be compared to the expected frequency under homogeneity, similar to the goodness of fit test. And because we're considering all the cells, we have to sum over all the rows, all the columns, and you compare each observed frequency to expected frequency, square that, and divide by the expected frequency. So you have your procedure in your textbook. There's your null hypothesis. The alternative is just that it's not true, so at least two PIs differ, or PIJs differ. The test statistic value, we've derived the formula there, and now the rejection region. Before I get to the rejection region, also remember the test can also only be safely applied as long as all the expected values, all the expected frequencies in each cell is at least 5. So this is quite important. And now the degrees of freedom. The degrees of freedom is I minus 1 times j minus 1. Now this is explained in the paragraph below, but let's just look at that. Remember, if we go back to table 13.9, this is basically the table. You have I populations. Within each of the I populations, you have j minus 1 uniquely determined cells, because all the frequencies, I wanted to look at this, no, not at this one. Your sample totals are fixed. So your last category is determined by the total and the first j minus 1 columns. So you have I independent populations, and for each of them you have j minus 1 degrees of freedom. J minus 1 because they all add up to the fixed total. So here you can see the number of degrees of freedom comes from the general rule of thumb, which says in each row we have j minus 1 freely determined cell counts. So that's I times j minus 1. But we also estimated P1 to Pj, remember, within P hat J is n dot J divided by n. So we had to estimate J parameters, but they all add up to 1. Therefore, it's actually J minus 1 parameters that are being estimated. So parameters P1 to Pj are estimated, but because the sum of the proper proportions is equal to 1, only J minus 1 of these are independent. So from this, we have I times J minus 1 degrees of freedom minus another J minus 1 degrees of freedom. And that is I minus 1 times J minus 1. And that's where this comes from. The degrees of freedom for your test for independence will also be the same, but it's determined differently. Here we assume fixed totals for each population. J minus 1 freely determined cell counts in each row, which gives us I times J minus 1. And from that we subtract another J minus 1 because the proportions all add up to 1. And now we can do an example. And I'm going to use exercise 26. Quite an interesting example because I report for both a sample of right-handed men and another sample of right-handed women, the number of individuals whose feet were the same size, had a bigger left than right foot, a difference of half a shoe size or more, or had a bigger right than left foot. So left bigger than right, left the same as right, or left smaller than right. For two independent samples, one size 40, one size 87. So this is N1 and this is N2. Does the data indicate that gender has a strong effect on the development of foot asymmetry? Now, you may wonder now, should this be a test for homogeneity or a test for independence? Another way that you can ask this question is to ask, that you can phrase this question is to say, is the occurrence of foot asymmetry the same for men and women? Or is the occurrence of foot asymmetry homogeneous for men and women? Now we have our observed frequencies and I've added the totals there. This is N.1, this is N.2, and this is N.3. This is N1 and this is N2, and this is the grand total for all our calculations. So what's our expected frequencies? The expected frequencies are row total times column total divided by grand total. Row total times column total divided by grand total. And then you have to work accurately enough so that your expected frequencies in total add up to the same as the observed frequencies. And now you can go ahead and calculate your chi-square test statistic. You compare your observed frequency to your expected frequency, square that value and divide by the expected frequency. And there you have your so-called cell chi-squared values. And the sum of all of them, in other words, 14.18 plus 0.16 plus 16.5 plus 6.52 and so on, gives you a value of 45. Now we've done all the calculations necessary for a two-way contingency table for a test for homogeneity, and we can perform the test. First step is gender are homogeneous with respect to the 3 foot asymmetry categories, or you can say the distribution of foot asymmetry is the same for both the gender. Versus the alternative that gender are not homogeneous with respect to foot asymmetry. So you can specify the null hypothesis in terms of words, or you can specify it in terms of proportions. But note now that we have two populations that we're comparing, male and female, and we're comparing 3 categories. So J is 1, 2, and 3. So let me just write down my other way that you can formulate the null hypothesis, namely foot asymmetry distribution is the same for male and female. Distributions are the same for the two populations, the distribution of the proportions. Okay, so in this case, no significance level is given, which means you have to interpret the p-value. And you will reject the null hypothesis if the p-value is small enough. Under the null hypothesis, we found that the chi-squared test statistic value is 45. We checked that all the expected frequencies are greater than 5. Let's just quickly check that again. Here you can see the expected frequencies are all greater than 5. Our degrees of freedom is equal to 2 minus 1 times 3 minus 1, I minus 1 times j minus 1, which is just 1 times 2, and that's 2. The p-value from table 8.10, you will see that the largest, 45 is largest than the largest value in that column, I believe, or row, whatever it is, but the probability associated with that is 0.001. And therefore, the null hypothesis is rejected, and we can say that sample evidence suggests that gender are not homogeneous with respect to foot asymmetry, which means the distribution of foot asymmetry is not the same for male and female. There's many ways to phrase a problem, and one unique way to write it out in mathematical symbols. So it's important that you understand the different ways to approach such a problem. What does the problem boil down to? That's what you eventually need to learn. Now there's a similar examples in your textbook, example 13.13 and also exercise 24 that you can work through. In this video, we consider the test for independence, which is the second test that we consider for the analysis of a contingency table. Contingency table, which forms the second part, section 13.3 of chapter 13. Our focus now is on the relationship between two different factors in a single population. The number of categories of the first factor will be denoted by I, and the number of categories in the second factor by J. Now this is similar to what we had in a two-way analysis of variance with one observation per cell. There we had I levels for factor 1 and we had J levels for factor 2. The difference being here that we work with counts and not with measurements. We're going to consider one sample of size n, and Nij will denote the number among the n who fall both in category I of the first factor and category J of the second factor. So it falls within both those categories at the same time. And now, for the test of independence with a single sample from a population, only the total sample size is fixed, and both the row totals and the column totals are observed values of random variables. So our table looks like this. These now are random variables as well, and these are observations of random variables. But these are our observed frequencies, only this is fixed. And that is equal to the sum of all the row totals, and it's also equal to the sum of all the column totals. So, for independence, what's our point of departure? We know in terms of probabilities what independence means, thinking back to chapter 2. And what we are working now with is a two-way contingency table. And for that, we're going to have to consider the proportion of individuals in the population who belong in category I of factor 1 and category J of factor 2, because that's what the frequencies are that we obtain from a contingency table. We have the number of individuals in the sample who belong in category I of factor 1 and category J of factor 2. So we need to determine the proportion, the probability of falling within this specific cell. So that's saying, in terms of probabilities, that this proportion of individuals falling in this specific cell is the probability that a randomly selected individual falls in both category I of factor 1 and category J of factor 2. Now, we can construct our table of frequencies. We can construct an equivalent table for the proportions and then see how the proportions relate to the frequencies. So here I have a proportion table similar to the frequency table in the previous slide, with total proportions P1 dot to Pi dot and total proportions in the columns P dot 1 to P dot J. Note that the proportions in the rows and the proportions in the column add up to 1. Now, and Pi dot, I've already indicated that that's the total of the proportions in the ith row, but it's also, if you want to interpret it, the probability that a randomly selected individual falls in category I of factor 1, ignoring factor 2. And similarly, P dot J is the probability that a randomly selected individual falls in category J of factor 2. Now, what do you know about independence and probabilities? You know that if two events A and B are independent, then the probability of the intersection is the product of the separate probabilities. Now we have an intersection here as well. Pij is the probability that a randomly selected individual falls within category I of factor 1 and category J of factor 2. So, probability of A and probability of B, using this rule for independence, means we can write probability in cell ij as the probability of observing a randomly selected individual in category I of factor 1 times the probability of observing that particular individual in category J of factor 2. And that will hold for every pair I and J, which means then the expected frequency in each cell is going to be the grand total times this probability, Pi dot times P dot J. And how can we estimate the probability in the ith row? We can take the total in the ith row and divide that by the grand total. So that will give us an estimate of the probability of a randomly selected individual being in the ith category of factor 1. And that's also P hat I dot then gives us the sample proportion for that category I of factor 1. And similarly, P hat dot J is what is the estimated probability of a randomly selected individual falling within category J of factor B or factor 2, and that will be the total in column J divided by the grand total. So that gives us the sample proportion for category J of factor 2. Now, how can we estimate the expected, how can we determine the expected frequency then? We get that by substituting these by their estimates, P hat I dot times P hat dot J. And there we have their estimates. And now you can see there's an N, there's an N, and there's an N. So what do we end up with? We end up with row total times column total times divided by grand total, just as we got with the test for homogeneity. Okay, so the test procedure for independence. The only thing that is different here is the null hypothesis. Also note that the null hypothesis is always the hypothesis of independence. The alternative is just that the null hypothesis is not true. Your test statistic is exactly calculated in the same way, and your degrees of freedom is now I minus 1 times j minus 1, because all the rows add up to n and all the columns add up to n. So you have I minus 1 independent row totals, and you have j minus 1 independent column totals, and that's your degrees of freedom. Also remember that your estimated frequencies must also be at least 5, your expected frequencies. And I've just written it down out again. Remember that the null hypothesis always states independence. So let me illustrate with an exercise, an example, and the example that I'll consider is exercise 29. Now we're considering political views and marijuana usage. Here you have a contingency table of college students. Now the total is not given here, but it's 1349. College students were classified according to their political views and their usage level. So that was factor 1, factor 2, and there you have the different categories for each factor. And the counts are given in the table, and we have to determine whether they are independent or not. Political views and usage of marijuana, is that independent or not? What would dependence mean? It may be that people with liberal political views tend to use drugs often or not. But the point is, does there seem to be the same distribution of usage level for each one of the political view categories? Because that would mean there's not really a difference. But if there is a relation between the political view and the usage level, we expect different distribution of proportions over the different categories of political views. So we expect differences in usage level for the different political views. So we're going to compare that to independence, under which we know exactly what to expect. So our observed frequencies, I take them as is, but I also get the totals because I know the test statistic value is dependent on these totals. My expected frequencies was obtained like that. You can see that I have to use enough decimals so that my totals agree in the end. And now, how did I obtain this? I obtained this expected frequency in row 1, column 1 by taking row total 1 times column total 1 divided by the grand total. Row total 1, column total 1 divided by the grand total. And another one, third row, third column, was row total 3 divided by column total 3 divided by grand total. So if we compare observed and expected frequencies, we get our cell chi-square values. If we take 479, subtract expected frequency, square it, and then divide it by the expected frequency again. Or row 3, column 3, we take 85, compare it to 49.03, square that difference, divide by the expected frequency again. So there's all our cell chi-square values. Let's just look at the expected frequencies. Due to our large sample, we don't have any expected frequencies less than 5, so we meet the assumption of the test. And what we can also see from all these cell chi-squared values is that it is the third category of both factors that contributes most to the test statistic value. So if we just go back to the original data, you can see that it's other political views with frequent usage of drugs that contributes most to deviation from independence. Our test statistic value is 64.654, which is rather large, but let's see whether it's large enough to reject the null hypothesis of independence. So we start with the null hypothesis. Either in words, the political views and marijuana usage level are independent, or we say Pij, probability in each cell is equal to the marginal probabilities, the product of the so-called marginal probabilities, against the alternative that they are not independent. In other words, the two factors are dependent. Given alpha is equal to 0.01, we know we reject the null hypothesis if the test statistic value is large enough. We have checked the expected frequencies, so we can work with the table as it is. We don't need to combine anything. All the expected frequencies are greater than 5, and our chi-square value is rather large. The degrees of freedom is I minus 1 times j minus 1, and it was a 3 by 3 table, so we end up with 2 times 2, that's 4 degrees of freedom. And you can see our test statistic value is much larger than that, so we will reject the null hypothesis. And we conclude that sample evidence suggests that political views and marijuana usage level are not independent. Now, before I conclude, you may have asked the question, what do we do if the expected frequencies are less than 5? Let's go back to this original table. Let's say we had data such as this: 47, 17, 11, 21, 4, 1, 17, 4, 8. Then you may find that some of the expected frequencies are not at least 5. And then you can decide on how to combine categories. You can either combine conservative and other, or you can combine rarely and frequently. If you look at these are the small frequencies. And you will have to decide what's going to solve your problem. Maybe if you combine rarely and frequently, you're still going to have a small number in here. It's going to be 5 and 12 if you combine those. While if you combine conservative and other, you will have 9 and 8. So it looks like you will be safe if you combine the 2 rows here rather than the 2 columns. But the same applies as with goodness of fit tests, that you combine adjacent factories. It must make sense. Conservative and other probably doesn't make, well, it may make sense to combine them, but for usage level, for example, you will not combine never and frequently because those are opposite ends. But rarely and frequently is closer to one another than never and frequently. So one has to be careful about how you combine these categories. It will be clear if we give you a problem, it must be clear whether it makes sense to combine either the rows or the columns. Otherwise, one can simply go and get a larger sample like the original one was. And then you don't have the problem with too few frequencies. So in conclusion, you will find similar examples in example 13.14 and exercise 40, which you can do as homework. Also note that the bottom of page 749 to page 751 are excluded ordinal factors and logistic regression. This is something that may be very valuable in your second or third year or even in honors, but for now it is excluded.